So, whenever you see sigma notation, it is the weird looking E symbol here. That is your Greek letter sigma. And then underneath it, you will see an index of summation. A lot of times it's an I. It's not always an I. It can be a different letter here, but a lot of times you'll see an I. It's not I like the square root of -1I. It's just the letter I. And so this is your start value. This is what number you are starting at. And then N is your upper bound. So that's the number you end at. And then you will have some sort of formula over here. In this particular case, I've just put a sub I. So what happens with the summation is you plug in those integers from your start value to whatever your upper bound is, until you're done. There. So let me give you an example. Sometimes it's a little easier just to see an example than it is to actually go through the textbook definition of it. So if I have the summation starting at 1 going to 6 of I, what I'm doing is I will plug in 1 into my equation that I have here, which is just I. So that means I just have a 1. And then I will put a plus sign, and then I'll plug in the next integer. So that'll be 2. And then 3. And then 4. And then 5. And then 6. For this. So what this symbolizes here is it's asking you to add up the number, all of the integers between 1 and 6 in this case. And so whenever we do that, let's see, what do we get? 6, 12, 21? Is that right? I had that right. Double check me on that. Yeah, I think so. Okay. Now that's a super simple example. Let's look at one just slightly more complicated. For this one, the integer that I'm beginning at is 0, and I'm going up to 5. And my formula this time is I plus 1. So this would be 0 plus 1, and then I'd add the next one. 1 plus 1, 2 plus 1, 3 plus 1, 4 plus 1, and 5 plus 1. And so you'll notice here that if I do what's in those parentheses there, I just get 1 plus 2 plus 3 plus 4 plus 5 plus 6, which also gives me 21. For that. So there's if I wanted to add the numbers between 1 and 6, there's an infinite number of ways that I could write that with a summation. Obviously, example 1 is the easiest way to write that with a summation, but you could use it with all types of formulas here. Okay? If I'm asked to evaluate the summation where j equals 3, and I'm going to 7, of j squared. So I told you we don't always have to use the letter I. So in this case, there's a j, but j is in your formula, so that's what you're replacing with that value. So this would be 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. We'll grab the calculator for that one. Actually, let's do this. I'm going to teach you how to use this calculator a little bit. You don't have to use it on the exam, but some of you may find yourself in Calc 2 having to use it, and I have not made you use it very much this year because we can use Desmos instead. So, let me pull up think Desmos does it too. If I want to do a summation, like, so obviously I just type this in here, but if I want to do a summation on the calculator, I'm going to do F3, and it's number 4 right here, which says sum, and I hope I've got it right. You're going to put in your formula. I'm going to use an X instead of a J, so X squared, and then comma 3, comma 7, I believe is what you do. You put your, let's make sure that works. No. What did I do wrong? Okay. It's not because I used X, is it? I don't think so. Oh, I bet I gotta tell it that X is a variable. I forgot to put comma X. Let's try that. Okay, there we go. Okay. So what I typed in here, let me, if you want to write this, I'm doing the sum X to the second, comma X, comma 3, comma 7. So you have to put the comma X there to tell it what the variable is. You could use whatever variable you want. Like if I wanted to use a J, I could use a J. X is just easier to type in on the calculator. And then you do comma start value, comma end value. There. And that adds that up for you, and you should get 135. So we can use the calculator to check ourselves on these. We do need to know how to do them by hand also, because the they may give, you're not going to see these on the exam much. They're occasionally on there. It's mostly something we have to learn, so we can learn limit definition, so we can get to the shortcut on this here. But I have seen a few where they use some summation stuff, and it might not be on calculator section, so we need to know how to do it without the calculator as well. 4 is not that bad to do without a calculator. It would be 6 times 1 minus 2 plus 6 times 2 minus 2 plus 6 times 3 minus 2 plus 6 times 4 minus 2. So that's going to be 10. No, that's going to be 4. Next one's going to be 10. 4 plus 10 plus 16 plus 22. And that would be 30, 40, 52. Okay. And when you're doing your assignment, I would like for you to try to do it by hand. Like, when I say by hand, like on this one, if you typed in 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared, that'd be okay. But you can also check it with the calculator. So, like, if I want to check this one, I would do 6x minus 2, comma, x, comma, 1, comma, 4. So check that there, and you get 52 that way as well. So, let's look at 5. 5 is going to be different. Because 5 goes from 1 to n, and k is our variable. N is actually like a number in this particular case. So this is going to be different. We're not going to be able to get like a final answer for this particular problem. So if I was asked to do this, this is what it would look like. I would have 1 over n times 1 squared plus 1. And then I would have 1 over n times 2 squared plus 1. I'm not replacing the n with that number because it's not the variable that we are using for the summation. It's just a constant of some sort. I'd have 1 over n times 3 squared plus 1. Now, this keeps on. I don't know what n is. I don't know where I stopped. So what I could do for this, what they'll do a lot of times is they'll do this. They'll do 1 over n times n minus 1 squared plus 1. Because n minus 1 would be the integer that comes before n. All right, it would be 1 less than n. And then they'll do, the final one would be 1 over n times n squared plus 1. Where n here is just my last number. It could be 8, it could be 10, it could be 27, it could be 1,000. I don't know what n is in this case. Now I'm doing this because I want you to see something that happens with this. Whenever I write out the summation right here, every single one of them has a 1 over n, right? And even the ones in the middle that I didn't write have a 1 over n. Is it okay to factor out the 1 over n in that case? That'd be all right. So I could write this with the 1 over n here, and then I'd have 1 squared plus 1 plus 2 squared plus 1 plus 3 squared plus 1 plus dot 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 plus n minus 1 squared plus 1 plus n squared plus 1.
Do you every time you stop, do you have to go to like could you just do 1 squared plus 1 and then dot dot dot, or are you supposed to do like 3, or does it matter?
I would at least have 1 and 2, so it's like obvious that you're going up by 1 there. If you left out that 3, I think it'd be okay in that case. So all of this stuff right here, if I wanted to, I could turn it back into a summation, right? So I could write this way. Now, it didn't tell me to write this back as a summation. I just want to point this out as we are looking at it. Your answer sort of for this would be this line that I just have right here. But I've got 1 over n, and I could write this back as a summation. It would be a summation where k equals 1, and we're going to n, and it is k squared plus 1. Now, if I compare what I have here with what I have up here, what does this teach us? What does this show us that we can do? I can just like move the 1 over n to the outside. Much like we did with derivatives and limits, if we were doing the derivative of 2 times f of x, we could just kind of keep that constant out front, right? So as long as this right here does not involve the variable that is changing, it can just sort of be factored out front and taken out front. So that is something that is going to help us a little bit moving forward with this. Okay, so if I look at example 6, there are going to be some shortcut formulas that we are going to have. And you're not going to see a ton of this on my test or on the AP exam, but there will be a little bit of this on the AP exam. So I will let you use any of these shortcut formulas on a note card, kind of like I did for that inverse trig stuff, mostly because it's just hard to remember and you're going to forget it by the exam anyway, so we'll just like cram it at the end. So this first shortcut formula, though, is pretty easy. Let's think about doing the sum from 1 to 3 of 5. Now, this one's a little bit weird because there is no variable over here. There's no k in this part of the graph. So if I plug in 1, what will I get? I just get 5. What about if I plug in 2? Still 5. And if I plug in 3, still 5. Because it's not 5 times k, it's just 5. It's 5 every single time. So this is just 15 here. So, a shortcut formula, if you're doing a sum of a constant, is that if you have the sum from 1 to n of c, where c is a constant here, your answer is just c times n, because it's that number added however many times there. For that, a couple things to make sure you pay attention to. I has to equal 1. I must equal 1 for that. Because if you're starting at 6 and going to 10, then that's not going to be 10. You're not going to add that number 10 times, right? It would be different. But as long as I is 1, then this shortcut rule applies. And you'll find that all of our shortcut rules are going to be for I equals 1. I'm not going to really give you anything much where I does not equal 1, unless I'm just asking you to evaluate like we did on those first problems. If I'm asking you to do this other stuff, then I'm going to give you I equals 1, because you can go really like far down this path trying to use summation notation for a lot of things, and it is difficult. And in the past I have tried to do more with it, and they don't put it on there a whole lot, and really just need a basic understanding, I think. So let's continue on. All right, this next shortcut formula. People say that Einstein could do this whenever he was, I think it was Einstein, maybe it was Newton, I don't even remember. It was one of the famous mathematicians. He could do this when he was like a child. It was, I think it was, no, maybe it was Newton. But like in grade school, he was bored, so his teacher asked him to add all the numbers from 1 to 100. And he did it in seconds. So I was teaching my class, I think it was a couple years ago, I was teaching my class about this, and I think Coach Wood had heard me talk about it earlier. And Coach Wood came in whenever he saw this on the board, and he told the class about the time that he was in grade school, and the teacher asked him to add numbers from 1 to 100 because he was bored. And then he told us about how he came up with this all on his own. But I'm pretty sure that was not a true story. So either Newton or Coach Wood won whenever they were a small child. Teacher asked them to add all the numbers from 1 to 100. Okay, so let's think about doing that. Let's think about adding all of the numbers from 1 to 100. All right, so if I'm going to add all of the numbers from 1 to 100, I would have 1 plus 2 plus 3 plus, this is going to keep on going, plus dot, 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 plus 99 plus 100. Okay. Can't remember it off the top of my head, but we're about to figure it out. Actually, let me do one thing here. Because I put 3 numbers here, let me make this, let's do plus 98, plus 99, plus 100. It's going to be important for what we're like coming up with here. All right, so this would be the sum from 1 to 100 of I. Okay. All right. Would 100 plus 98, or 99 plus 98 plus dot, dot, dot plus 3 plus 2 plus 1. Would that also equal the sum from 1 to 100 of I. Right, order doesn't matter. It's fine if I start with 100. I mean, the way you're thinking of doing it is you're going to start with 1, 2, 3, 4, but the numerical value of it's the same whether I do from 1 to 100 or 100 to back to 1, right? So these are equivalent to each other. All right, so let's think about doing this. What if I add these together? Okay, so if I add 1 and 100, I get 101. What about if I add 2 and 99? 101. What about 3 and 98? 101. Dot, dot, dot. That's going to continue. 98 and 3. 101. 101. And 101. This would be 2 times the sum from 1 to 100 of I. Okay, so what I've got here is I've got 101. How many times are they being added? 100, because you got to think about the dot, dot, dot in the middle, right? So the dot, this should be 100 numbers. So this is 100 times, right? If we count all of them together. So this would be equivalent to 101 times 100. That would equal twice the sum from 1 to 100, right? So 10,100 would equal 2 times the sum from 1 to 100. And then if I want to know, I don't want to know twice the sum from 1 to 100. I want to know just the sum of the number of integers from 1 to 100. What would I have to do last? Divide by 2. And that would give you 5,050 would be the sum of the numbers from 1 to 100. And Newton or Coach Wood figured this out whenever they were just a lad long ago. Okay, so what I would like for us to do is to generalize this even more, because I would like a general rule I could use, whether this is 1 to 100, or 1 to 5, or 1 to 5 million, or 1 to 7, right? I want a general rule I can use. So let's take this same reasoning, but let's change a couple things, and you can change it on yours if you want, or just watch, because this is the reasoning that goes behind the shortcut rule is what we're getting to. So let's say it's not 100 anymore. Let's not do 100. Let's change 100 just to n, because n could represent any number. Right, so I'm going to change my 100 to n. Okay, that means that these numbers right here would not necessarily be 100. My last number would have to be n. All done? Okay. I'll take your work there. And I'll get that ready and get back to you. Okay. So if this is n, what's the number that comes before n? N minus 1. And what's this number? N minus 2. Okay? So I'm going to have to erase some of this right here. And I'm definitely going to have to erase my 101s. right here. Okay, so this would be n plus n minus 1 plus n minus 2. Okay, so if I do the same thing that I did before with 100, what do I get whenever I add these two together? N plus 1 or 1 plus n. I'm going to do n plus 1. What about when I add 2 and n minus 1? I got 2 plus n minus 1, and I can combine my 2 and my negative 1, which is going to still give me n plus 1. And over here, still n plus 1, dot, dot, dot. Same thing's going to happen over here. I got n plus 1s all the way across. Okay? So, how many times do I have n plus 1? Not 100 this time. N times. Because we're generalizing and we're making it however many, if n is 7, it's 7 times. If n is 20, it's 20 times. Here. Okay, let me get rid of this because this stuff only applied to 100. Okay, so if I've got n plus 1 n times, that could be written like this. N times n plus 1. So, actually I'm going to erase this. This is a mess right here. So now I've got n plus 1 equals 2 times the sum from 1 to n of I. If I want to have just the sum from 1 to n of I need to get rid of that 2 just like we did before. Divide off that 2. And so now, n times n plus 1 over 2 equals the sum from 1 to n of I. And you can see that's what we've got down here in our shortcut box. Okay, so whether it's 100 or whether it's 1,000,000 or whether it's 2, we can use this formula to find the sum from 1 to that number here. So it's a shortcut for doing these problems. So like if I look at example 7, I've got it written twice because there's 2 ways you could do it. You could do it like I showed you already. You could do 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9. That is one way to do the problem. And if I add those together, let's see, I got 10, 20, 30, 40. I think you get 45. Okay. Or I could use my shortcut formula, which would be, I would do my n, which is 9, times n plus 1, which is 9 plus 1, divided by 2, which would be 9 times 10 divided by 2. So 90 divided by 2 would be 45. Now, for that particular problem, I don't know that the shortcut is necessarily that much quicker, right? It's not, there's not a big difference in how difficult this is. But if this is not calculator active, the shortcut a lot of times is significantly quicker than adding all the numbers together if you have really large numbers for that. Okay, questions here? Alright, there are 2 more shortcut rules. We are not going to go through deriving the shortcut rules because what I was doing here, if you decide to major in math in college, this is an example of some of the stuff that you'll talk about a whole lot. Like, rather than just saying, oh, here's the shortcut rules, yes, Miss Hyatt, I believe you, and I'm going to use it. If you major in math, a lot of what you do is like reasoning through why things are the way they are, and you've got to like prove that that's the case. these do have proofs for them. I don't know them. I might could figure them out, but I'm not going to go through how to do either one of these. But these two shortcuts also might need to be used. After we finish notes, I'll give you a note card. You can put all of these shortcut rules on that note card, and I will let you use that on the test. This is not going to be tested heavily. It's a stepping stone to get to where we need to go. But it could be on there a little bit. So if I have this example here, I've got the sum from 1 to 10 of I plus 1 over n squared here. If I'm doing this problem, did I mean for that? I think I meant for that to be an n. If I'm doing this problem, I could use the shortcut rules to help make it a little bit easier. You could also do it the long way. You could do 1 plus 1 over n squared plus 2 plus 1 over n squared plus 3 plus 1 over n squared. It's not the worst in the world to do, but I would like for us to work on these shortcut rules because we're going to need them to be able to do the limit definition that we're going to look at tomorrow. So if I use the shortcut rules, first of all, this n squared is not the indexed variable. It's not the I in this case. What could I do with that n squared so I don't have to mess with it? I can bring it to the outside, so that would be 1 over n squared out here. And then that would be multiplied by the sum from 1 to 10. Oh, what's happening there? Of I. What is going on? It's like right and sideways. Let me try this again. Okay. The sum from 1 to 10. Put that. 10 of I plus 1. Now, you can figure that out by hand. It's not the worst in the world to figure out by hand, but I want us to use shortcut rules for this. So, when I'm doing this sum of these two things right here, I could break it up into the sum of from 1 to 10 of I plus the sum from 1 to 10 of 1. I could break up those sums. And then I can use my shortcut rules to answer this part of the problem. So I'd have 1 over n squared. It just hangs out front. It's going to be there the whole time. And then if I want to use the shortcut rules instead of listing it all out, the shortcut rule for just an I was n times n plus 1 over 2. Or I guess I should use, because they put an n in this problem, let me use I. It's going to be, well, let me just use the rule. N times n plus 1 over 2. So n is 10 for this case, so it's going to be 10 times 10 plus 1, which gives me 11 over 2. That's what I will get for this piece right here, using that shortcut rule. And then the shortcut rule for a constant is just that we take that constant and multiply it by our end value, which would be 10. So if we just simplify that down a little bit, we're going to have 110 over 2 plus 10, which is 55 plus 10. So I have 1 over n squared times 65. They might write it like this. They might do 65 over n squared. And that would be as simplified as you could go because the n's a constant that we don't know. Okay, questions? Okay. let's look at another one. Okay, so for this example, this is where it really starts, like shortcut rules are a lot faster for this. I've got the sum from 1 to 15 of n times I squared minus 1. Going from 1 to 15 and having to square everything is going to take a while if you don't have a calculator. So for this, I would take the n out front here, and I would also split up this sum. So it would look like this: n times the sum from 1 to 15 of I squared minus the sum from 1 to 15 of I. I'm sorry, not I. What should be there? 1. Okay, so we can use those shortcut rules, and honestly, I don't even really know them that well. For I squared, it's n times n plus 1 times 2n plus 1 all over 6. So we're doing n times n plus 1 times 2n. Was it plus 1 or minus 1? Plus 1. All over 6. This is your I squared rule. So it'll look like this. You'll have 15 times 15 plus 1, which gives us 16, times 2 times 15 plus 1, which gives us 31, all over 6. That part right here will be this part right here. Then we must also do the second part. This is just the constant. So your constant shortcut rule is to take your constant and multiply it by your end number. So this would be what you get right here. Okay, so in this case, you got, I still don't want to use, I'm still going to use the calculator. It's still bad. Maybe not quite as bad as having to do 1 through 14 and square them all and add them together, but still bad. So 15 times 16 times 31, there is going to be 7,440. Divide that by 6. We're going to get 1,240 for this part, minus our 15. N is still out front. And if you subtract that 15, you'll get 1,225. And then you'll have the N there. So that would be our answer for that. Two times 15 plus 1.
Oh.
Yeah. Okay. Whenever you get to your homework, some of the first ones are going to be very small, very easy. You can calculate them out by hand. When you get to some of these that have a lot of squares and bigger numbers, I would like for you to try to use the shortcut rules for that. Okay. One of the last things you're going to be asked to do on your homework is you're going to be asked to write the expression with sigma notation. So you're going to have 1 plus 2 plus 3 plus ... plus 6 plus 7, and you're going to have to write sigma notation for it. Some of these will be pretty easy. Some of them are kind of tricky. So like this particular case, you got your sigma. What number are we starting at? 1. What number do we stop at? 7. What variable goes over here? Just the I, or K, whatever variable you're using there. Okay. The key to doing these problems, A is pretty straightforward. The key to doing these problems is to look at what is changing. So like if we look at B, Actually, I shouldn't even highlight that square right there. The only thing that's changing is the 4, 5, and then it ends up at 9. Right? That's what's changing. That needs to be your variable. So like my equation that I'm going to have here is going to be I squared plus 1. And then I'm going to start, for this one, do I start at 1? I start at 4 instead. Where do I end? 9.
So you write down beside the thing of what's changing, like what?
Right, so whatever number is changing is your variable. So you're basically going to take like one of these pieces right here, because they're all separated out by plus signs, and you're going to change whatever that was that I have highlighted there, change it to your variable, change it to your I, and that is your equation that goes over here on the side. Okay, I think when you get down to C and D, this gets kind of difficult. What is changing in C? Okay, in the second parentheses, it's the numerator of the second fraction, right? Because this goes from 1 to 2 to n. They don't give you a lot of stuff to go with there. So it's a little hard to tell, but that's what's changing. So when you write this here, you're basically going to take one of these, and that highlighted thing is going to turn into your variable. I think I'll use a different variable here just to show you that you can. Right? So like I'm going to do 1 over n times 6 plus, let's call it k over n here. And so if I call that k, then k is going to equal 1 here. What's my ending number? N. For that. Now you could use an I, you could use a j, you could use whatever. Alright, so our last one here, you're looking for what's changing. Similar to the last problem, it's that numerator of that fraction. That's what's changing. So the summation for this one would be the sum from 1 to n of n times the square root of 1 plus I over n squared. Okay, questions? All right, this has something to do with Riemann sums, even though it doesn't feel like it so much right now. So, your assignment, pull it up, I think I got it on Canvas here, is, yes, it is tomorrow. I'd almost forgotten it's tomorrow, but it is tomorrow. We need to go over one, don't we? What'd you say? No. Sorry, good idea, but I don't think so. All right, so your homework tonight is going to be page 299, 1 through 23 odd. These should not be like having to do 12 related rate problems. They should be quicker than that. So 299, 1 through 23 odd. And we do need to go over FRQ because I almost forgot that it is tomorrow. We might have time. What are we on, 15? Yeah. We skipped 14 on purpose. 14 was one that we are not going to do. 14 was the progress check for Unit 4, so we've done it. We just didn't do it as an FRQ quiz. All right. Have you guys had time to look at them? Which one do you want to do? is the key posted?
Yeah.
The whole key?
Yeah.
For some reason, I don't have the whole key saved
The
there.
whole key is in Canvas.
Okay, good. I don't, but they're on Canvas, so you can just write it on notebook paper. Look at it there and write it on notebook paper. Okay, let's go through this here. So, g of x is x e to the negative x plus b e to the negative x. B is a positive constant. So the first thing they ask us for is the limit as x approaches infinity. What you need to do here is, because you have negative exponents, is you need to write this as fractions. So what we're really doing here is the limit as x approaches infinity of x over e to the x plus b over e to the x. Okay, so if I look at these two right here, if I have x over e to the x, limit as x approaches infinity, that's my Bobo-Botno, ECC, right? If I have x over e to the x, is that bigger on top, bigger on bottom? Exponents are the same. Which one is it? It's bigger on bottom because e's, exponentials overpower x to any power, right? Exponentials grow faster. So that would be 0. What about b over e to the x? Same thing. It would also be 0. So you're just going to get a 0 here for that. And I feel like I had more written on that key, but that's all you, no, that's all right. All I got.
On the key, all you did was change it, show that you changed it from the negative exponents to the fraction.
Yeah. So that's all you got. All you really have to do there. Yeah. And you're kind of doing these two limits separately since they got a plus sign in between them. But this one's bigger on, and e to the x is bigger than x to any power. So this is big. Both of those are bigger on the bottom and are going to go to 0. Okay, and that's all you really got to do for that. That part's not too bad. All right. Then it's going to ask you, for what positive value of b does g have an absolute maximum at x equals 2/3? Justify your answer. So if we think about maximums or minimums, for maximums or minimums, we need to know where the derivative equals 0, and then at a maximum, our derivative switches from positive to negative. And hopefully it only switches one time here, because if it does more than once, then we're going to have some trouble proving its absolute maximum. But maybe it just switches one time. So we need a derivative. We need to set it equal to 0, find some critical points, and think about a maximum. So my function is g of x equals x e to the negative x. Is it plus or minus? Plus b e to the negative x. So when I take the derivative here, what have I got to use to take that derivative of x e to the negative x? Product rule. Because both of those pieces have an x. So you got to take this piece as your first part and this piece as your second part. So you are going to do x times the derivative of e to the negative x. The derivative of e to something is e to that something. But you've got to use a chain rule here for your exponent. What's the derivative of the exponent? -1. So I'm just going to put that negative out front, right there. Plus, then you'll have e to the negative x times the derivative of x, which is just 1. So this takes the derivative of that first part. We also have to do the derivative of b e to the negative x. Do I need a product rule here? No, because b is a constant, right? So I'm just going to have b, derivative of e to the negative x is e to the negative x, but you have to do the chain rule with that exponent. Derivative of the exponent is negative, so I'm actually just going to take this right here and make it a minus instead. I'm noticing that each one of these terms has an e to the negative x. So it would be a good idea to factor out e to the negative x. And that would leave us with a negative x plus 1 minus b. So this is our derivative. Once we get our derivative, if we're thinking about maximums or minimums, we have to set this equal to 0. Is e to the negative x ever going to equal 0? It will not. E to any power is just always going to be positive. But negative x plus 1 minus b equals 0. You can set that equal to 0. There's something there, but we've got too many variables to solve it, right? So at this point, we want to stop and think about what are we trying to prove? Actually, we know what the derivative should be at 2/3. We should have a maximum at 2/3, which means my derivative should be 0, right? So at x equals 2/3, I should get 0, right? So if I plug in for x, if I plug 2/3 in for x, then I can solve for b in this case. So I would have negative 2/3 plus 1 minus b equals 0. Negative 2/3 plus 1 is just 1/3 minus b equals 0. If you add the b to the other side, b is going to equal 1/3. Now, I do need to show this as an absolute maximum. So, if I think here, if b is 1/3, right, then g prime of x equals e to the negative x times negative x plus 1 minus 1/3, which if I simplify a little bit is e to the negative x times negative x plus 2/3. So on my sign line, 2/3 goes here. It's not 1/3 because this is a sign line where we have x right here. And if I plug in a number smaller than 2/3, such as 0 right here, I will get a positive right there. And if I plug in a number bigger than 2/3, like 1, negative 1 plus 2/3 would be negative over here. And so since we only have one critical point right there at 2/3, and we switch from positive to negative, we have a relative maximum, but it has to also be the absolute because it's our only critical point there. So you would say since g prime of x changes from positive to negative at x equals 2/3 and is the only critical point G has an absolute maximum at Questions there? All right. Last part is point of inflection. What do we need to know for point of inflection? Second derivative. So we got to take the derivative of our derivative here. Now, it is important that it says find all values of b, if any, for which the graph has a point of inflection. So that means we're not plugging in 1/3 for our b. We got to go back to this derivative that we had here. So our g prime of x was e to the negative x times negative x plus 1 minus b. And I am definitely going to run out of time here. Let's see if it'll let me pull up my key. 299, 1 through 23 odd. Let me just pull this up and see if I can go through my key more quickly. Yeah, so I did a quotient rule on, did I do a quotient rule on that one? No, I did, but I did put it like that. So I made this over e to the x on my key. You can do it that way, or you can do a product rule. It doesn't matter. But you're going to have e to the x times negative 1 minus 1 minus x minus b times e to the x over e to 2x. You're going to do all this work. I don't think this is like where we're going to be the most in trouble right here. You're going to set those equal to 0. So if you solve this for x, x equals 2 minus b. So here, it did tell us b was, I think it told us b was a positive integer. So if I plug in 2 over here, then if I plug in 2 into that derivative, I'm going to get b over e to the x. That's going to be positive for that. To get something smaller than 2 minus b, I did 2 minus 2b, because if I double however big that b was I was subtracting, that's going to be a smaller number. And if you do that, you'll end up with negative b over e to the x, so that's going to be negative because the new b was a positive integer. So then you are going to say, because this changes signs, you have a point of inflection. And that point of inflection would be on this interval here. So it's tricky because you've got to plug in like values with b.